Okay, here we are in a brand new video, and on the left it's about this diagram, and I represent that this is not my diagram. This is not my unit circle, and it's not my triangle. I got this out of a textbook, an engineering textbook. It was first printed in 1926, and it was titled Mathematics for Engineering, and it was by the authors were Raymond and Robert Dull. So it was by Dull and Dull, and it was published by McGraw-Hill. So moving on, all I did to this was to program it so that it could be interactive for the purposes of intuition. And so let's see what that looks like. Over here on the upper left hand side, I can find my cursor. Here it is. If I can find my cursor, this controls the angle, and there the angle has changed. Okay, so you get some intuition about what's happening with the values by seeing the angle change, and see how it affects the quantities involved. So here I'm going to point out two things. I'm going to say that right here they have the symbol A. The way they're using this symbol in this instance is pretty special. It's something to point out, and something important to kind of keep track of. So they're using this symbol right here to represent the measured distance between the center of this circle and this reference point. And then up here they say you see, and that's a to the first power. Now here you see a, and it's the exact same value of a, but only raised to the second power. Okay, so this green line segment is shorter than this black line segment. So how could that be? Well, if you pay it, if you look here, this is a unit circle, which means the hypotenuse is a length of 1, which means if it's the longest side in this triangle, that all of these other line segments are fractions. Well, a fraction times a fraction is always smaller. An example is 1/2 times 1/2 is 1/4. Well, for the value of a, it's a fractional number, so if you square it, it's going to be a line. It's going to be a value that's shorter, smaller, so the line segment's going to be shorter. So here we have a value, fractional value of a to the first power. Here we have a fractional value of a to the second power. Same thing over here for b. B is representing the symbolic value. In other words, it's not a numeric value, but it is a value, and you treat it the same way you do numeric values. You can raise numeric values to powers. Well, so can you do with symbolic values. So the symbolic value of this measured line segment between these two reference points right here, these two red reference points, is a value. When you multiply that by itself or raise it to the second power, like we've done here, this is the same value b raised to the second power, and this represents the symbolic value of the distance, measured distance between this reference point and this reference point. So another thing to point out is this is a standard A, B, C triangle. Now because C equals 1, it's also going to equal to C squared. So C equals 1 and C squared equals 1. Anyway, I saw this in this diagram, and I was curious about how they used this back in 1926. And apparently they scaled this drawing, draw it to scale, and then they could use a divider to transfer measured line segments that had a mathematical relationship between each other of to the one line segment to the first power, and the other line segment the same base to the second power. The same way here would be, you could have a line segment that was this length transferred by a divider, and then you could have the same quantity b raised to the second power, and you can transfer its line segment to a drawing. So anyway, moving on. I'm going to go over here to the right and go full screen. And in this we have the exact same diagram, but we've got the angles labeled. What happens is when you put I'm going to represent that this is a base to the hypotenuse. Here's the hypotenuse, and this is a base to that hypotenuse. When you do that in any right triangle, you get three triangles: the smallest one, the medium-sized one, and the biggest one that you started with originally. And basically they all have the same angles, so they're what we call similar triangles. Well, a neat thing happens with similar triangles. You have corresponding sides, ratios of corresponding sides are equal. So let's see what that looks like. Down here, if we have the adjacent side and the hypotenuse side for the large triangle, and the adjacent side and the hypotenuse for the medium-sized triangle, then their ratios, this ratio is equal to this ratio. Okay, so let's see how that works. Okay, so for the large triangle, adjacent over hypotenuse, for the large triangle here, the adjacent side is A, and the hypotenuse is C. A over C. So the adjacent side over the hypotenuse for the medium-sized triangle, let's see what that looks like. Okay, so here is the medium-sized triangle. Okay, and right here, D is the adjacent side, and the hypotenuse is right here, so that's A. So it's D over A. Now in your cross multiply, you're going to have a squared term. I wrote that down here. And your other cross term, you're going to have one which is the identity element. In other words, the identity element is when you, as a number, when you multiply times anything, you get that thing back. So 1 times D is D. So D is equal to A squared. So that's the reason why up here I can write A to the second power. In other words, if A represents the length of this line segment, measured line segment, then this is the same quantity raised to the second power. It represents the distance between these two reference points. Okay, moving on. Over here, for the hypotenuse, ratio of the hypotenuse, opposite side to the hypotenuse of the large triangle. Okay, so here's the large triangle, and the opposite side is over here, which is B, over the hypotenuse, which is C. Okay, so that would be B over C. And over here for the small triangle, we're looking for the opposite over the hypotenuse for the small triangle. Okay, here's the small triangle. Let's see what that would look like. The opposite side is E, and the hypotenuse for this is right here, which is B. So it'd be E over B. E over B. Okay, when we cross multiply here, we get a squared term. Which is equal to E times the identity element, or same thing as C. That's this cross multiply here. So this being equal to this, I can write B squared is equal to E. Okay, so I'm going up here and I'm going to write B squared. Okay, that's the end of the video. It basically shows how A squared plus B squared is equal to the hypotenuse. Since C is equal to 1, it's also equal to C squared, because 1 squared, so C equals 1 and C squared equals 1. So I thought that was a pretty neat relationship, and I just wanted to share it with everybody. That's the end of this video, and I'm going to get out of full screen here, and we've got just a little bit more over 10 minutes. Anyway, thank you, and have a good day. Bye.